What we see is this, that a single excitatory postsynaptic potential, EPSP, is typically not strong enough to bring the neuron to that threshold voltage of negative 55 millivolts. So typically, a single EPSP is going to be somewhere in the neighborhood of 0.5 millivolts. And of course, you realize that we need 15 millivolts to go from the negative 70 resting membrane potential to the negative 55 millivolt threshold potential. On this particular slide, we see the effects of various presynaptic neurons on the membrane potential and the postsynaptic neuron. Now, if we go to the left-hand side here, we see that A would be an excitatory presynaptic neuron, B is an inhibitory presynaptic neuron, A excitatory, B inhibitory, and so on. And so what we notice is that we don't show an action potential. An action potential doesn't occur until we reach threshold, as you know. And we reach threshold if you're following the pointer at this particular place on the slide. And there are reasons for that. So one thing that we're going to notice is that all presynaptic axons don't have equivalent input or don't have equivalent influence on the charge that's found in the postsynaptic cell. And we'll explain why in just a moment. But the end result here is that the membrane potential of the postsynaptic cell is the result of the action of all the synapses that it forms with its presynaptic neurons. And so there are thousands of these, most likely, hundreds of which are active at any given moment. And some of them are excitatory, some inhibitory. And what we notice is that the important thing is that final charge that's reached in that initial segment, also referred to as the axon hillock. Now, as you would imagine, what is really important here is something referred to as summation. And so summation is essentially what we just described. It is the ultimate membrane potential that's reached as a result of the input of all of these different presynaptic neurons on the single postsynaptic neuron. What we want to look at on this particular slide are the two types of summation that can occur in the postsynaptic neuron. To do that, let's take a look at the figure that's found on this particular slide. And first, let's look over here at the drawing on the left-hand side. So we have a single postsynaptic neuron following the pointer on the screen here. We have a recording electrode that's placed inside it. And we have three, to make things fairly simple in this case, presynaptic neurons that are synapsing with and influencing this single postsynaptic neuron. Two of these, the two labeled A and B, are excitatory. One of these, C, shown in red here, is inhibitory. Now, let's go to the graph, and in the graph, we're going to see what happens when we stimulate A, B, and C at different intervals. Now, of course, the graph shows the membrane potential at this recording electrode that's placed inside the postsynaptic cell. And if we start at the left-hand side of the graph, what we see is that if we send an electrical signal, an action potential down A, and that's what's being done here, we send an action potential down A, then it does influence the postsynaptic cell, and it does create some depolarization in the postsynaptic cell, but not a whole lot. And because, as you know, these synaptic potentials are a type of graded potential, and they're very transient, they go away very quickly, then that rapidly fades away. So at this point, we stimulate A again, and we get a nearly identical depolarization in the postsynaptic cell. So essentially, nothing has happened. We have stimulated the postsynaptic cell twice. We've created two graded potentials. Of course, the type of graded potential we created is a synaptic potential, and they've disappeared, so no overall effect has been endured by the organism in which we find this neuron. So in other words, the organism doesn't know that it's being stimulated because no action potential made its way back to the central nervous system. Now let's go to 2. So in 2, here on our graph, we do something different. We stimulate A, just like we did before over here in the beginning of our graph, and we get the same depolarization we observed here, but the difference is the time interval that elapses before we stimulate A again. So here, we only allow a very short period of time to elapse. We apply a second stimulus, and what we see is that we get a second graded potential, but that graded potential is of greater magnitude than the one we achieved over here because we started with a higher baseline. We hadn't gone all the way back to that resting membrane potential. You may say, well, that doesn't make sense because of the refractory period that we learned about. But the refractory period, remember, that only deals with those voltage-gated sodium channels, that are found in the axon of the neuron. So these are different channels. These are ligand-gated channels that are binding to a neurotransmitter. So there is no refractory period that's in play here at all. And it would make sense, this temporal summation makes perfect sense, doesn't it? Because we have this neurotransmitter that's binding, it's opening these non-specific, most likely, sodium and potassium channels. Sodium is rushing in, and then that sodium is not pumped out. It doesn't have a chance to be pumped out before we have a second stimulation. So then these channels open again, perhaps additional channels open as well, and we have increased depolarization above what we would have had if we allowed a greater amount of time to elapse between these two stimulatory impulses. And again, it's important to note that these are both stimulations that are coming down, both action potentials that are coming down neuron A in this particular case. So we refer to this as temporal summation because it depends on the time. We can see that this occurred, this summation, this greater change in the resting membrane potential occurred as a result of the time that was allowed to elapse between the two stimulation events in A. So that is temporal summation. Let's go over to part 3 of our graph. In part 3 of our graph, what we see is this. Excitingly, we stimulate the neuron here, but we're stimulating it with B, with this different presynaptic neuron. And so when we stimulate B, we get some depolarization there, then we go back to threshold, and then, look at this, we stimulate A and B simultaneously. And when we do that, as you would expect, we have a greater concentration, a greater overall volume of sodium that flows into the cell, so we have a greater change in the charge in the postsynaptic cell. So this is spatial summation, because we have two presynaptic neurons in the same general area that are stimulated, and obviously they have to be stimulated pretty close to the same time, but when they are stimulated, then they open a greater number of channels than would be opened if just B is stimulated by itself, so we have a greater degree of depolarization. Now, so spatial summation, to summarize. Now, moving over to part 4 of our graph here. What we see in part 4 is this, that we are experiencing both temporal and spatial summation here. So we're stimulating A, B, B. And what we see is that we have this progressive increase in charge up and up and up and up as a result of the opening of all of these ion channels and the rushing of sodium into the cell. And this does allow us to achieve that negative 15 volt depolarization, or that 15 volt depolarization, all the way up to negative 55. And then the voltage-gated sodium channels open and the action potential commences. And so we go all the way up to positive 30 and exhibit that action potential as we've learned about previously. So, as you know, backwards and forwards at this point, the only important thing is if you reach that threshold voltage of negative 55 millivolts. Lastly, if we go to part 5 of this particular graph, what we see is this. Here we're stimulating C, presynaptic neuron C. Presynaptic neuron C, as you can see over there, is an inhibitory synapse. And so it, of course, as we talked about previously, is either opening just potassium channels or potassium and chloride ion channels, or perhaps just chloride ion channels, and it's causing this hyperpolarization of the cell. So what we see is that neutralization can occur if we stimulate A, shown here, C, shown here, simultaneously. A is exciting, B is inhibiting, and so the ultimate result is they cancel each other out, and we have stabilization of the resting membrane potential. And we call this neutralization because the excitatory and inhibitory synapse have neutralized one another. The last thing we want to point out regarding synaptic integration is this, that when a synaptic potential occurs, this type of graded potential, then, let's go down to A here at the excitatory synapse. And so what's happening in A is that we have a signal that's released We open up these sodium ion channels. Sodium rushes into the postsynaptic cell and it spreads out. Now, it doesn't go too far, but it does spread in this direction, as you can see, following all these arrows. As you well know at this point, the really important part of the postsynaptic cell is this initial segment, also known as the axon hillock. And so the axon hillock has this threshold voltage of negative 55 millivolts. Interestingly, the rest of the cell does have, the rest of the neuron, like where I'm pointing here, does have a threshold potential, but it's generally much higher than negative 55 millivolts. So it's very unlikely that an action potential could be achieved on other parts of the neuron. And what we notice is that as these positive charges, sodium ions, reach this initial segment, then we have this depolarization that you're familiar with, and that's where summation comes in. If we have enough of these stimulatory events, we can eventually reach threshold. Now, the initial segment has this negative 55, this lower, which is good, makes it more sensitive and more likely to undergo an action potential threshold voltage, because it has a higher density of these sodium channels, these voltage-gated sodium channels that are found within it. And I did mean to say voltage-gated, right? So the voltage-gated channels are the ones that are going to open and initiate this action potential. These are ligand-gated channels, as you know, over here, that are causing this synaptic potential. And what we see is that the input of all presynaptic neurons is not equivalent, and you can see that very easily by looking at this particular diagram. So you could imagine, although it's not depicted here, that a presynaptic neuron that synapses on this side of the postsynaptic cell would have less influence. In other words, it would be less likely to initiate an action potential than would a presynaptic neuron that terminated, say, right here, where I'm placing the cursor on the screen at this moment. Simply because these charges spread out within the postsynaptic cell, but they dissipate. And so you know that from our discussion of graded potentials and how they rapidly dissipate. They don't move very far. They're decremental. They go away very rapidly within the postsynaptic cell. So this means that presynaptic cells that have their axon terminals closer to the initial segment, also known as the axon hillock, will have a greater influence on the postsynaptic cell. The last point that we want to make in this particular section is an important one, and it's this, that these postsynaptic potentials, also just known as synaptic potentials, last much longer than do action potentials. Action potentials move very rapidly and, of course, are limited by the characteristics of the sodium channels and the refractory periods, but these last longer. And so what we see is that there's no picture here of this, but I'm going to go ahead and point to this initial segment as I speak. So if this initial segment remains depolarized after the firing of the first action potential, and so the charge is above negative 55 here, an action potential fires and moves on down here, the sodium ion channels, where I have the pointer now, go through the entire refractory period, and then they're ready to fire again, and the charge is still above negative 55 millivolts. Well, then another action potential is going to fire. And the reality is that although that may not be how we've thought about it, as we have learned about it so far in this chapter, action potentials almost nearly fire in these short bursts, as opposed to a single action potential at a time. In other words, a postsynaptic neuron, like the one that we have pictured here, will undergo depolarization to threshold, and then bam, 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 it'll fire several action potentials. Those action potentials run in close succession down the axon to their target, and then, of course, the cell will become repolarized, and the action potentials will cease to fire. But the overall message that we want to get across here is that action potentials typically come in short bursts as a result of the fact that these synaptic potentials in postsynaptic cells, we could call them postsynaptic potentials, last for a fairly long period of time, relatively speaking, and therefore that's long enough for multiple action potentials to be initiated before the initial segment repolarizes.